Okay, we're going to look over the forces to math part of the lab. So first let's put down the equation, which is going to be force drag equals 1/2 QCAV squared. Now, I'm going to write this twice because we're going to have to use this twice to find the terminal velocity for the smashed and for the non-smashed. So I'm going to go ahead and write that here. FD equals 1/2 QCAV squared. So, yeah, okay. So let's get the force drag is just going to be, we're calculating the terminal velocity right now. So the force drag pushing up when it's at terminal velocity, that's going to be pushing up. So that's the force of friction pushing up on the item falling in the atmosphere. And then the force of gravity is going to be the thing pushing down. So we're going to get force of gravity pushing down, force drag pushing up, and those will be equal whenever we have terminal velocity. So no acceleration. That means this vector is just as strong as that vector, or that force vector is just as strong. Those are just as strong, but they're in equal and opposite direction. Okay, so I'm going to put mass times acceleration here equals 1/2 QCAV squared. Same thing on this side. Mass times acceleration equals 1/2 QCAV squared. Now the mass, let's look for the mass. We got 4.5 grams for the piece of paper, and the quarter is 5.7 grams. So the mass of the total object is going to be 4.5 plus 5.7. Add those two together, I get a 2, 1, and then 5 plus 1 plus 4 plus 5, that equals 10.2. But remember, that implies 10.2 grams, not 10.2 kilograms, right? So let's go ahead and make that unit conversion right now before we forget. Okay, so grams to kilograms unit conversion. Okay, we have 10.2 grams, but we need a K there. We need kilograms, 1,000 grams. So let's put this all divided by 1, because we can divide it by 1, no problem, and that won't change the value. And then we're going to multiply it by 1, which also will not change the value. Remember, K, that is literally 1,000. That means 1,000. So if we divide K by 1,000, all this is just 1. So we're just multiplying this by 1, which will not change it. Okay, so I'm going to move that K right there in the next step. So I get 10.2 kilograms divided by 1,000. Now we need to move this decimal place over because we are dividing by 1,000. So we need to move it over 3 times. 1, 2, 3. So 0.0102 kilograms is going to be the total weight of the coin and the paper together. Okay, so let's zoom in here and put that in for both of them. 0.102, is that 0.0102. 0.102 times acceleration due to gravity, which is 10, equals 1/2. What is Q? Q is on Earth, right? So let's look at that real quick. What is that going to be? We only have 2 Q values in this chapter. And so we have Earth, which is going to be 1. On Mars, it's 0.55. Okay, so Q is going to be 1. Now we need the C value. So this is going to be, let's say this is smashed. So let's look for the smashed C value. Okay, we're going to read it. use 1.2 for the C value of the non-smashed piece of paper, and look up the C value for a sphere for the smashed piece of paper. Okay, so non-smashed. Okay, so let's do non-smashed here. And let's go ahead and fill this out because we know the C value for that. Okay, 0.0102, we know that's the same. If you smash a coin around a piece of paper, it's going to weigh the same exact amount as if you just let it fall without smashing, right? It's just other things are going to change, like the C and the A value. Okay, so times acceleration due to gravity, which we already know is 10. 1/2 Q, it's on Earth, doesn't matter. But this is non-smashed. So non-smashed, we get 1.2. Now that makes sense. That really makes sense to me because look, if you are looking at the C values for things moving in the air, we get a piece of paper. Whoops. Oh, it's just falling down. Now let's look at what would be similar. What would be most similar to a piece of paper? This would be most opposite. An airfoil is something perfectly, like almost perfectly aerodynamic. It's really aerodynamic. Maybe a piece of paper would look like a circular flat plate. So a flat plate would look, something like that falling down. So those are going to be similar, just a flat plate and a square. It just turns out that this one has a C value of 1.2 and this has a C value of 1.12. So those are similar. But if we were to drop a sphere, so I need to color this in. Let's see if I can shade it. I'm going to attempt to shade. Anyway, that's a ball. That's supposed to be a sphere. That's supposed to be round. It looks different, right? It's a sphere or a ball or a marble is going to fall through the air differently than a piece of paper. Okay, and then if you were to smash this paper up, let's try to make smashed paper. Here, imagine this is a ball of smashed paper. Then that's going to be more like there we go. That's the smashed paper. That's going to look more like the sphere, right? That's going to change the C value because this is all about shape. C value is all about shape. Okay, so let's go over here. We changed the C value. Now let's look for the C value for the smashed. And it looks like it says look up the C value for a sphere for the smashed piece of paper. So which we kind of already did. So sphere 0.45. Right? Check it out. 0.45. All right. So C value for the smashed is 0.45. Let's go ahead and separate these guys a little bit. Okay, and then we get the area. So the area for the smashed one. Okay. The area of a piece of paper is about 0.06 meters, non-smashed. So let's put that in the non-smashed category. Area, 0.06 v squared. Okay, and this one, the area, it looks like it is smash the paper to 1/10 of the area. So we got to divide 0.06 by 10, but it looks like it's already giving it to us, 0.006. Okay, times 0.006 v squared. Okay, separating these out a little bit again. Okay, so let's go ahead and simplify both sides. So I'm going to simplify the left side of the smashed. So we're looking over here now, and we get 0.102 once we simplify this whole thing. Now I'm going to go ahead and plug it into my calculator, all of this here. Okay. One half multiplied by 0.45 times 0.006. And I get 0.00135 v squared. I'm going to divide both sides by 0.00135. All right, now I got v squared being 75.6. 75.6. So what I'm doing is I'm just 3 significant digits. I don't want to do anything more accurate than that because this is physics, not engineering. So now what I want to do is take the square root of both sides. And so v equals the square root of 75.6. And remember to do the plus or minus. And I get about 8.7. 8.7. Now I made a small mistake here. Should be negative. And I left something out. Should be in meters per second. Okay, so this next one, let's go ahead and simplify this one. So 0.102. 0.0102. Multiplied by 10, which is going to be 0.102, equals, now again, I'm going to have to use the calculator for this one. And I got 0.036 v squared. Now we got to divide both sides by 0.036. And I get 2.83. Take the square root. And I get 1.68. And remember that should be negative and meters per second. Okay, so I'm looking here at the smashed, and I get 8.7 meters per second. And then if I just imagine that, what that looks like, 8.7 meters per second at terminal velocity. Okay, that makes sense. And then now here, I get a smaller velocity downwards at negative 1.68 meters per second. That makes sense that this one would have a smaller magnitude than this one. All right. Well, let's see if there's anything else to talk about here. Right, so this will have some implications on your lab. Yeah, I guess I won't give out anything more, but there you go. That's the math part that some people were asking about. All right.